were initially going to be like, what is the word? Asynchronous. Like, you guys were going to do this on your own. But here we are. We're technically a day behind because look at the scheduled date there. I don't think we're the 14th today, right? Yeah, so we're technically a day behind, but that's fine. No big deal. We'll catch up next week. We'll use Tuesday as a notes day, and then we'll call it a day. We'll be back on track. All right, here we go. A super quick lesson on horizontal asymptotes. Don't be a robot. It's all about end behavior. So if I have a function like y equals 3x squared plus 5x plus 2 over 5x squared plus, I'm just making something up. If you spit in the ocean, does the ocean rise? No. So it's the same thing with functions. What's ocean? What's spit? Well, in this expression, this rational function that I have here, the 3x squared in the numerator would be ocean, and the 5x plus 2 would be spit. Yep, the 5x squared would be ocean, and the one, I don't know what that, 100,000 would be spit. So your end behavior, whenever you see EB, that stands for end behavior, is 3x squared over 5x squared. Guess what cancels out? So my end behavior is 3/5. That means this would have a horizontal asymptote at y equals 3/5. That's all it means. If you were to type this into the calculator, 3/5 is a decimal 0.6, right? So look, I just want you guys to see. So here's my TI-84. You don't have to write any of this down. This is my, I still have your calculator, miss. Yeah, do you remember? Sorry, miss. Yay, see, that one's a pretty one. No, but it's okay. I like that color. Miss Kyle, it's okay because you can't use that on the SAT anymore. You don't have to. No, that one you can. That one you can. You can't use the CAS in the SAT anymore. Check it out. What was the I already forgot the fraction I had. Oh no, but the original 3x squared plus 5x plus what? And on the bottom I had what? 5x squared, no? Plus like 100,000 or something. Oh, 10,000. I can't tell the difference. Okay, check it out, guys. I'm gonna tell the calculator to give to me in decimal because right now I have it in. So where it says answers, I'm just going to put des. Make sure you know how to use your calculator. So check it out. I'm going to go to second table set, and I'm going to go to independent. I'm going to put ask. I'm going to push enter. Look what happens. Remember that 3 over 5 is 0.6, right? Look what happens. I push 1. I get a number. That's a really small number. I push 10. I get another number, 0.03. I push 100. 0.50. I put 1,000. 0.599. Put another. It says 0.6. It's not 0.6, guys. If you hover over it, look what it is. But I'm approaching 0.6. So it's probably going back and forth, up and down a little bit, because I can see I was below 0.59 and I'm a little bit above 0.6 there. So it's probably going like horizontal asymptotes you can cross. But you can see what I'm approaching as x gets larger and larger. It's approaching 0.6. Does that make sense, guys? Okay. So I just want you guys to see that. Yeah, let me see what's going on here. Usually, okay, well, it doesn't matter. I probably have yeah, we're fine. All right, so yeah, that's, by the way, if the degree of the denominator is bigger than the degree of the numerator, my horizontal asymptote would be 0 because that's my end behavior. The bottom's growing faster than the top. Chop, I have no idea what you're talking about. Look, 1 divided by 1 is 1. 1 divided by 10 is 0.1. 1 divided by 100 is 0.01. 1 divided by 1,000 is 0.001. Look what's happening. It's approaching 0. As the bottom gets larger, and I know that my numerator, I left it as a constant, but as long as the bottom is growing faster than the top, you're going to be approaching 0.
So if it was like, say the 3x squared was in the numerator, it was just 5x, and then over 5x squared, the vertical asymptote would be 0?
Horizontal.
The horizontal asymptote.
Yep. So that's end behavior, guys. And if the numerator grows faster than the denominator, you don't have a horizontal asymptote. Does that make sense? Okay, perfect. So there it is. Okay, last thing. Do we know how exponential functions look like, especially e to the x? Here it is. Y equals e to the x looks like this, guys. So as this approaches infinity, as x approaches infinity, y approaches infinity. As x approaches negative infinity, y approaches 0. Does that make sense? All right. I think we know enough. Let's see. Letter A, limit as x approaches negative infinity of e to the x. Well, here I have it. I have it right there. 0. You guys see? All right, now this one says limit as x approaches infinity for e to the negative x. Okay, let me write how that one looks. E to the negative x looks like this. Let me write it in blue. It looks like this, guys. And don't be a robot. Make sure that some of you just memorize things. Make sure that we understand why. Maybe in a little bit when we do the base of a 2, you'll see why. So this one is a 0 again. You guys see that? All right, ln of x. How does ln of x look like? Ln of x looks like this. You have a vertical asymptote at x equals 0, and it goes up forever at a slow rate. It's the inverse of e to the x. But it still increases as x approaches infinity. My y values still get bigger and bigger, just very slowly. So as x approaches infinity, ln of x approaches infinity, just very slowly, but it still approaches infinity. Does that make sense, guys? Okay. So now I have ln of ln x. It's still going to approach infinity, just super, super, super slow. Slow as a snail. Because the rate of change of ln x is a really small number to begin with. Like, see how it's kind of already flat? So now I have ln of x inside of ln of x, inside of ln. So look, we can type. Yeah, we can type it in. No big deal. Look, ln, and then inside of that, I'm going to type ln of x, and it's going to grow, but just very, very, very slow, super slow. Look how slow it's growing. 0.8, 1.52, 1.93, 2.44. Let's put a whole bunch of zeros here. It's still growing, just really slowly. Let's put a whole bunch of zeros until your heart is content. Look at that. It's still growing, just super slow because you have ln inside of an ln. Does that make sense, guys? So I know this is one of those trickery questions, but this is still, so as x approaches infinity, this is going to be infinity. It's still growing. All right, let's see if we can figure this out right here. Look at this. Oh, I don't know what's happening, Chop. Guys, it doesn't matter that I have 0.001. I have the exponent is still negative, so it behaves like this. Just the exponent part, e to the negative x. So this part right here that I'm circling, that is going to approach what? No, not infinity. 0, just what I circled. So what's 1 over 2 plus 0? 0.5. 1/2. I'll say it again just in case. Yeah. This 10 e to the 0.001x, it has a negative in it. That's approaching 0. So this is going to be approaching 0.5. In case you have issues, in case you're like, oh, I don't see it. Look, let's type it in the calculator. Check it out. I'm going to close y equals. I'm going to push the fraction feature. And I already forgot what I had in the bottom. What was it? 2 plus e to the 2 plus 10e. Okay. Negative point. I'll go ahead and change it right now. 0.001. And then there was a 10 in front of the e. So let me put that 10 in there. Second, insert 10 plus 10e. There. Now I got it right. Looks funky though. All right, it doesn't matter. Look, second table. Well, hold on, it's not. Where's my x? Oh yeah, I am missing the x. How come you guys didn't tell me before? You guys made me look like a dummy. I was already questioning life choices. All right. Look at this, guys. Look at that. And no, it says 0.5. It's not 0.5. If you have, it's the tolerance of the calculator is not very good. If you have a CAS like your calculator will probably be a little better. The TI-84 is the best calculator for testing, in my opinion, because of the buttons. But if you have all day, you want the strongest calculator. CAS is always stronger. The laptop is always stronger, like MATLAB or Maple or Mathematica. It's not 0.5, guys, but it's really close to 0.5. It's just that there's so many zeros, so that's going to say 0.5, 0.5 as well. All right. Cool or not cool? Did you sleep, miss? All right, look at letter F. End behavior, guys. End behavior. You're not going to have to FOIL all this. All you care about is the biggest term. 7 times x times x. So my numerator, limit as x approaches infinity, 7x squared is your ocean. Everything else would have been split. You don't have to do the other stuff. In the denominator, it's x squared. So what's going to be my answer? 7. Do you see what we did? What about letter G?
0.
0. Why is it 0, Miss Houston? Because the denominator is growing. Perfect. Yeah. The denominator is growing faster than the numerator. What about letter H? Well, yeah, there. No, well, look at the degree. What's growing faster, the numerator or the denominator? So there is either right does not exist or infinity. You're not converging to any number. It keeps growing bigger and bigger and bigger because the top is bigger than the bottom. Chop. Yes. I'm going to make the denominator constant to make life easier. 1 divided by 1, 1. 10 divided by 1, 10. 100 divided by 1, 100. 1,000 divided by 1, 1,000. I know I'm making the denominator constant, but this is the same logic. As long as the top is growing faster than the bottom, the output will get bigger and bigger and bigger. The magnitude will get bigger and bigger and bigger. So I'm not converging to any number. That's why it does not exist. I just keep growing unbounded. Does that make sense, guys? The better answer is infinity because of the behavior, but does not exist is a perfectly acceptable answer. Are we cool? Okay. What about letter I? 7 over 2. All right, here we go. End behavior. Relax. We are approaching, x is approaching infinity, so the end behavior of the numerator is 5x. The end behavior of the denominator, you're going to square the x value, and then you take a square root. The x squared is the ocean, and the x squared plus 1,000 minus 24. What's the square root of x squared? X. So this becomes what? 5. Yes, but look at what x is approaching. All right, so let's talk about it. Let's think about it. So here it is. End behavior for this one, letter K. So put your pencils down. Just take it all in, guys. So here you go. Ready? No, look, check it out. I have, what is x approaching? So in the numerator, I have 5 times a negative number. Are you guys cool? So my end behavior for the numerator is a negative 5x. Why? Because I'm multiplying by a negative number. Are we clear on that? All right. In the denominator, you're squaring that negative number, and then you're taking the square root. So in the denominator, is it going to be negative or is it going to be positive? So I'm just going to write positive x. Does that make sense? So this one, what is it going to approach? Negative 5. Yes, for like this. Yes. Yeah. You know what? Maybe some of you are saying, why didn't we do that for letter I when we did it? You could have done it for letter I. This is, and this one here. And then, but look, negative 7x cubed. Well, actually, letter I is a positive infinity. But if we were to approach negative infinity, you know what? Don't worry, I'm going to explain it again, Ms. Rodriguez. So let's say I had limit as x approaches negative infinity for this one. 7x cubed plus 34x minus 3.59 over 2x cubed minus 350x plus 3.51. If I would have had negative infinity for this one, it wouldn't have changed anything because in the top, end behavior, negative 7x cubed over end behavior again, because it's an odd function, negative 2x cubed. What's negative divided by negative? So I still would have had 7 over 2. But on this one, why does this one change? The square root. When I square the square root, you're squaring it first. Do you see what I mean? I guess it's the same logic step, maybe. But I don't want to say it's the same but you know what I'm talking about, right?
So you just have to make them both negative, but because that one makes
I made it both negative because x is approaching negative infinity. But yeah, you're right. The bottom's being squared, so that one turns positive. Do you see what I mean? Okay. If you don't like that, relax. I do want you to do it without a calculator. But if you don't like that, look, here's the calculator so we can see it. I already forgot what I had in the numerator. So what was it? 5x, right? And then in the denominator, I had square root of x squared plus what? Plus 1,000? That was it? Just that? Let me look at it. Oh, minus 24 on the outside. Okay, got it. Sorry, guys. Minus 24, like that. So check it out. Second table. There it is. As I approach positive infinity, that 5 is not really a 5. Let's see if it does it this time. See? And then that one, yeah, there's just way too many zeros. Look at that. 1 with 29 zeros followed. That's crazy. Now let's see what happens when I approach negative. So here we go. Negative 1. Bam. Look at that. It's negative output. Negative 10. Bam. Look at that. Negative 100. Bam. Negative 1,000. Bam. Negative. Do you guys see what's going on? Look, it's approaching negative 5. Cool, right? You could also look at a graph, but let's see how this graph looks. See? Horizontal asymptote of 5 and negative 5. How do we feel, guys? Okay. Let's see. Now let's talk about this. Oh, yeah, please. If it was cubed, the domain would not be part because of the negative, right? You can't take a square root of a negative number. We wouldn't, because of the domain restriction. So we wouldn't even have anything there to begin with. So there would be no limit. You know what I mean? Okay, here we go. Do we know the graph of y equals e to the x? Y equals 2 to the x. Both of these behave similar. E to the x, what's e to the x? What's the value of e? 2.69 or 2.71? Look, here it is. Second e. Oh, second quit. Second e, enter. 2.71, 2.72. So that's what e is. So both of these are going to look like this. And I chose 2 to the x on purpose because 2 to the power x, you guys are familiar with that because of binary and computer science and all that good stuff. And plus, you've been exposed to it all your life, right? Like the memory of your phone, RAM. Do you guys know what I'm talking about? 2, 4, 6, 8, 16, 32, 64, 128, 256. Do those numbers sound familiar to you? Yeah, it's like, look at the memory of your iPhones. It's always by those numbers. Oh, look at the memory, the RAM memory. Like, why is it always those specific numbers? Because of binary, 0 and 1. There's only 2 options. So that's why it's 2 to the power. That's why the increments always happen like that. If you're like, oh, why that number? Why 512? Why 1028? Because of that. Yeah, no, you're good. You're good. Do you guys know what I'm talking about? Do you guys see that? Okay. So, and notice, so look, as x gets larger, this gets bigger. And as x gets smaller, this approaches 0. Why? Well, because look, 2 to the power negative 1, that means this. That's a half. 2 to the power negative 2, that means this. That's a fourth. See? And look how it's getting 2 to the power negative 3, that means 1 over 2 cubed. That's 1/8.
Does it matter the number or will the behavior stay the same? So if I had like y equals 6 to the x,
The graph will look the same. Of course, the output will be different because it's a different base. But the graph will look relatively the same. Does that make sense, guys? Okay. What happens? So now look at this one. 1/2 to the power x. Well, I could have rewritten this one. If I bring this up, I would. Say that again? Okay. Check it out. Let me put this in blues because I don't want you guys to get confused. So if I write this up, if I bring this up, 2 to the power negative 1 to the power x, then remember your laws of exponents. Whenever you have an exponent to an exponent, 2 to the negative x. OMG, this one's going to look like this, guys. Why? Because I'm just looking at this graph right here. The one in red. Well, now I'm circling it in blue. If I make that power 1, it's a half. If I make that power 2, it's a fourth. If I make that power 3, it's an eighth. Look what's happening. As x gets larger, the y value is getting smaller and smaller. Do you guys see that? So that's why 2 to the negative x is going to look like this. Because as the x gets larger in magnitude, the output is going to be approaching 0. Bam! Everyone get some sleep. Does that make sense, guys? I know. We've had a tough week. You guys woke up super early this morning. All right, so here you go. What happens if we add a transformation? Well, if we put that negative up there, well, you already see what happened. Right? What's up?
Sorry, I thought it asked what was y equals 2 to the power of x, not y equals 2 to the power of x.
Oh, y equals 2 to the power x looks like this one.
Oh, I thought that was e to the x.
It also, They all look relatively the same. The output's going to be different, but all the graphs. Let's go to Desmos real quick so you guys can see it. I have Desmos open already, I think. Oh, never mind. I thought I did. Look, Desmos. Y equals 2 to the power x. See, looks like that. Y equals e to the power x. See, they all look similar. Obviously, they're going to have different values because it's a different thing. You said 6 to the power x. Y equals 6 to the power x. Look, I put y. I put 6 to the power x there. See how they all look similar? But as soon as I put a negative, y equals 2 to the power negative x. Oh, look at that. By the way, that's the same. That's the same as saying 1/2 to the power x. Look at the black one and look at the purple one. It's the same. OMG, how is it the same? Because of that property that I just talked to you about. You know? We cool? Okay.
So then what would it look like y equals negative?
Well, yeah, that's which one are you talking about? If you put a
Third one.
like the third one, well, if you put a negative in the front, all that does to your outputs is turn them negative. So they were positive, now they're negative, so they reflect across what? The x-axis. Those are your properties. So no, hopefully we're no longer robots. You're starting to see why certain things happen. What's up? Yeah, if you make the say it again. No, if you make the exponent negative, you're still the outputs are still positive, right? That's what we look. That's what we said with that purple one. See, I'm still above the x-axis. It reflects. Oh, it reflects across the y-axis. You didn't say x-axis. Sorry. Yeah, it reflects across the y-axis. But do you see like why? And okay, Kyle, you see what's up? Are you good? Are you good? Okay, I'm gonna say are you good, my G, but I'll stop. G stands for gangster, right? Okay. Oh, okay. I'm not in with the hood or whatever, you know? I don't know what they call it. All right. One of these days, I'm going to come up with my channel, Hood Math. You guys know what I'm talking about? All right, here we go. Here we go. So what happens with this one? You already know, guys. We just talked about that's just going to look like this. E to the x minus 4. Well, that's e to the x with a vertical shift of down 4. So instead of being, okay, by the way, I guess I'll draw two of them. Y equals e to the x looks like this. Where this point right here, that's 0, 1. So if you bring that point down 4, now I'm going to be where? Yeah, negative 3. With a horizontal asymptote of negative 4.
Why is it at 0?
Because anything raised to the power 0 is 1. So e to the 0 equals 1. Does that make sense? For this one, y equals e to the x. And then when you move minus 4, that point goes down 4, so that's 0, negative 3. With a horizontal asymptote of y equals negative 4. So let me put that in there so you guys can know. Y equals negative 4 is horizontal asymptote. So if they were to ever ask you, because they will, limit as x approaches negative infinity of e to the x minus 4 without dropping a beat, I would like for you to say negative 4.
So if it was x minus like 7 with the horizontal asymptote, then 3%.
Yes. Because my horizontal asymptote of the original is y equals 0. And then you just drop in it. So, you know. All right. This one here, Chav, I don't know. Well, y equals 2 to the x. Y equals 2 to the x looks like, let me change the color. Y equals 2 to the power x, and that looks like this. So what do you think happens when I insert a negative right in the front? So it's just going to look like this. All these are just principles from your algebra days. You can figure it out by just thinking about it for a little bit. Are we cool? All right, so here we go. Let's see if we can do this without a calculator, and if we need to use a calculator, we will. I'm approaching infinity. I have 2/3, and I have the negative x. So that negative x is like saying 3 over 2 to the power x. So as x gets larger, what do you think happens? Yeah, it increases. And I know you guys are visual learners, so let me bring it out. So let's clear all these. So what did I have? Y equals, yeah, or was it 2/3 or 3/2? Y equals parenthesis 2/3, close it, to the power negative x minus 1. Minus 1 was also on the power, right? It's not going to let me. Let me put it up. Yeah, x minus 1. And that. And did it have any other transformation? Minus 2. There it is. Look what happens. Make sure we understand why, guys. I don't want you to be a robot. Make sure that negative there, pretend that minus 1 is not there. It's not going to, when we're talking about infinities, we don't care about that minus 1. It's that negative x that we care about. So that negative x is like saying 3/2 to the power x. You know what I mean? Because that's like bringing law of exponents 2/3 to the negative 1. You know, does that make sense? Or just think about that negative x. Think about that 2/3 and what happens as x gets larger. Chop, what are you talking about? Okay, think about a decimal. Let me give you the decimal. 0.5. 0.5 squared is 0.25. Well, 0.25 is smaller than 0.5. 0.5 to the 0 is 1. 0.5 to the 1 is 0.5. 0.5 to the 2 is 0.25. 0.5 to the 3 is 0.125 to the 125. Look what's happening. It's just getting smaller and smaller. That's what's happening here. As long as the number, the base, if your base is between 0 and 1, and you have an exponent of negative, as long as that x value gets larger and larger, you're going to get smaller, because a number between 0 and 1, when you square it, when you to the third power, fourth power, fifth power, the output, the y value just keeps getting smaller and smaller, because you already got a small number and then you're multiplying by another. That makes sense, guys? Yeah. Sometimes that's a hard concept for you guys, for anyone, period, even teachers. I've seen teachers struggle. And the best way that I can think about it is pretend like one is pretend you're making copies, and it says, what's your scale factor that you want to copy? If you make the scale factor 1, all your copies come out the same. If you make your scale factor 1.5, all your copies are going to be slightly bigger. Or it's like zooming in, for those that are in camera. If you make your scale factor 0.5, all your copies, the image is going to be smaller. You guys see that? So whenever you multiply by a scale factor that's smaller than 1, of course it's going to get smaller and smaller, because you're multiplying by a magnitude that's smaller than 1. Okay, sorry guys. All right, look at number 12. I have 2/3, and again I have negative x's in there in the top, and I'm approaching infinity. And there is a negative in the front of that. So what is that going to approach? Negative infinity. Good job. Good job. All right, look at this one. So let's just think about this. 0.4 to the power x. As x gets larger, this output is getting smaller, right? Do you see it? Okay. Now I have a negative in the front there, and I'm approaching negative infinity. So, okay, so I guess we're not approaching, where x is not getting smaller. X is not getting bigger, it's getting smaller. 0.4 to the, chop, I'm confused again. You're confused me. Okay, look. 1/2 to the power x. I'm going to put a negative in the front. So let's just use 1/2 because I think we're good with this one. If I make x negative 1, that means it's 1/2 and then 2, bring it up. I'll do a table right here, and I'll erase it. Just listen, guys. Don't write this down. If I make negative 1, that 1/2 turns to 2 to the power 1. Do you agree? If I make negative 2, that 1/2, that means 2 to the negative 2. That means I'm going to have an output of 4. Do you agree? If I make negative 3, that means 2 to the negative 3. And when I bring it up, it's going to be 2 to the third, so it's going to be 8. What's happening to the outputs? No, check it out. The outputs, 2, 4, 8. They're getting bigger. So when I approach negative infinity, because that's what this one is approaching, this output's going to be getting bigger. The magnitude's going to be getting bigger. But because I have that negative in the front, it's going to be what? Negative infinity. Okay. Does that make sense, guys? Okay, if it didn't make sense to you, you could always do what? Go to Desmos, and let's type that in really fast. Y equals, I have a negative in the front, parentheses, 0.4, close to the power, what was it? X, and then minus 1 in the bottom? Minus 4. I mean, it doesn't really matter. You can already see it. What's happening as I approach negative infinity? Negative infinity. Do you guys see that? Yeah, see, there it is. All right, so let's see this one. Now I'm approaching. You already saw the answer. I'm approaching positive infinity. So this is going to be approaching 0. That part right there, just what I circled. And then when I subtract 4, this is going to be approaching what? -4. And I already have the graph right here, so you can see that it is in fact approaching. If I put it right here, Chow, how do you know that's -4? Y equals -4. It is in fact approaching that green line. I know it looks like it touches. It does not. It does not. If you zoom in more and more, look how cool this is, man. If you zoom in more and more, that lines that we're touching are no longer. Cool, right? Okay. No, they will never. So even if you go to positive infinity, you zoom in again, they will be different. A little. Okay. X approaching infinity of 3/2. But notice I have a negative x. So that's like 2/3 to the power x. So that's going to be 0 here. -2. That's going to be approaching -2. Do you guys see what I did there? Okay. 3/2 to the power x. I know there's a -1. Relax. If I approach infinity, does this ever converge? No, it's a number bigger than 1. It's just going to keep getting bigger and bigger and bigger and bigger. So this is going to be positive infinity. How do we feel? Don't worry, we're going to do some more. Well, that's all for end behavior, so we have a delta on that. But let's finish this part out, and then we'll call it a day. Bless you, bless you, bless you. I think I have it due Sunday, but if you have trouble with it, just let me know. All right, let's approach x equals 3 from the left. Write out an expression in limit form. Okay, if I approach 3 from the left, here's 3. What do I get? Negative infinity. Limit as x approaches 3. I put a 3 from the left of this function is negative infinity. Let's approach x equals 3 from the right and write out an expression in limit form. Limit as x approaches 3 from the right of this function equals, if I approach 3 from the right, it is positive infinity. And then I say, observe the behavior as we approach an infinite discontinuity. More on discontinuities in notes 2. How are limits related to asymptotic behavior in this situation? Okay, if I have, so notice I have vertical asymptotes. So if your behavior is negative infinity or positive infinity from one direction, you have a vertical asymptote. That's all you got to, that's the main thing here. So if limit as x approaches c from the left of some function equals positive infinity or negative infinity, comma, x equals c is VA, is vertical asymptote. Same thing, by the way, sorry, what's up? I'm about to right here. Limit as x approaches c from the right of f of x equals positive infinity or negative infinity. X equals c is VA. You might have positive infinity from one side and the other one might be an actual value because you have a infinite discontinuity and it's a piecewise function. All right, so putting it all together, what can we conclude? For horizontal asymptote, let me change it back to red.
So does if the limit approaches just c, either from the left or the right?
It's not if the limit approaches c and you have an output like a value, a limit, and an L, then you don't have an infinite discontinuity because you're approaching a value. All right, horizontal asymptotes. If horizontal asymptotes only apply for x approaches infinity or negative infinity of some function. If you have a value, and I'm going to say L for limit, then y equals L is horizontal asymptote. Does that make sense, guys? I'll say it again. Don't worry, because I know we're going fast. I'm trying to race against the clock. Think about it. I'll slow down. If you approach infinity or negative infinity and you have a limit, that has to be a horizontal asymptote. It has to. Because you're converging to a number. And that's the definition of a horizontal asymptote. Does that make sense?
Yeah.
Okay. Now, if you're approaching a specific number, let's talk about vertical asymptotes. If you're approaching a specific number, limit as x approaches c from the left, or limit as x approaches c from the right, and you get infinity or negative infinity, it's a vertical asymptote. Then x equals c is VA. Pretty much I'm just stating this again. again.
So let's say it like approaches 4.
Well, what approaches? If like x approaches 4,
And like say limit at if c from the left.
limit as x approaches 4 from the left of some function
Yes.
equals,
And it equals like 4.
then it's not a vertical asymptote because it equals the number.
Okay.
So you're approaching a value. You got to approach infinity or negative infinity to be a vertical asymptote. Yeah, because of, you know what I mean? Like you don't cross vertical asymptotes, so that's why you either go positive infinity or negative infinity. Does that make sense, guys? Okay, you're not just going through the motions, right? All right, that's it. We're done. Take care of the delta. Ask me questions. Let me pass back your handouts from last time. I already graded them all. And good job, guys. We did good today.